at which that heat flow is occur. And at a certain point, if I want only a certain temperature to be attained, how much time would it take? That's the kind of question we'll ask. So it's a subject which is dealing with the rate at which heat flow occurs. That's the distinction between what we study in thermodynamics and what we study in heat transfer. Now, why is it important? Why is it important to study heat transfer? It is important because once we have these laws which govern the process of heat transfer, we will be in a position to design equipment, size equipment in which the heat transfer process occurs. Now, let me give an example so that you'll understand what I mean. All of you have sat in a car. All of you have seen a car radiator sitting in the front of the car. If you open the bonnet, right in front there's a very small rectangular box-like structure which is the car radiator. What does the car radiator do? The car radiator receives hot water which has come from the engine cylinder walls. That hot water typically is at about, say, 95 degrees centigrade. And that hot water is cooled by air which flows over that radiator, cooled by 5 or 10 degrees, and then again circulated around the cylinder walls. So the hot water picks up heat in the cylinder walls and gives up heat in the radiator. And this way it maintains the cylinder walls at a particular temperature, safe temperature. In the radiator, it gives up heat to the air which flows over it. That air is pulled by a fan which is behind the radiator. So the purpose of the radiator is to take away heat from the hot water and give it to air which is the environmental air, the surrounding air. That device, the car radiator, is a heat exchanger. To be able to design that heat exchanger, you need to understand the process of heat transfer, the convective process of heat transfer occurring on the air side, occurring on the water side, the conduction process that is occurring in the fins and the tubes which make up the radiator, and then only can you design that car radiator. So the whole object of study heat transfer is to be able to design size devices in which heat transfer takes place. And the car radiator is a good example because, as you well know, millions of car radiators are made every year for the millions of cars which drive us all over the world. So that's just one example to illustrate why this subject is of importance. So during this course, we'll be deriving such equations in convection, in radiation, in conduction, so that we can design heat transfer equipment. By design, I mean find the appropriate size for a given end state that you are desiring in your fluid. We would be able to size heat exchange equipment and be able to do elementary design. That's the whole object of this, teaching this subject. Now, let me move on to mass transfer. Just like I said, in heat transfer, if there is a temperature difference, we know that heat flows from the region of high temperature to the region of low temperature. Similarly, if there is a concentration difference, we know that mass moves from the region of high concentration to the region of low concentration. Now let me again take an example. Take this room. This room contains air, oxygen and nitrogen in a proportion of, say, 4:1 typically. Nitrogen, oxygen in the ratio of 4:1 approximately. All right. Let us say in the corner there, in that room, at the top there, I hold a cylinder of compressed gas of nitrogen and let some nitrogen out. Obviously, in that corner, top corner there, the concentration of nitrogen in the air is going to increase, going to be higher compared to the concentration elsewhere in this room. What will be the net result if I let out a certain amount of nitrogen? Immediately that nitrogen will move and diffuse in this room so that eventually the concentration will again be uniform in this room. There is a high concentration of nitrogen there, there is a lower concentration here. Nitrogen will move in this direction, will diffuse in this direction so that that concentration difference is reduced. So mass transfer occurs, in this case the mass being transferred is nitrogen. the species being moving is nitrogen. Mass transfer occurs when there is a concentration difference. Heat transfer occurs when there is a temperature difference. All right. Now, mass transfer is important also in a variety of processes. For example, to give you an example, let us say we have to dry a particular surface, a film on a particular surface. This is done all the time in many pieces of equipment. We have a film of liquid, we need to dry it. In order to dry that film, you pass air over that film, and the air picks up the film of water or liquid, whatever it is, evaporates into the air, and mass transfer takes place and it dries. What is the rate at which that mass transfer will occur? What should be the size of that surface so that I will be able to get the required film thickness totally removed by the time the air moves over a certain region over that surface? These are the kind of questions we have to answer in order to size mass transfer equipment for a particular purpose. So, when we study mass transfer, we will be able to design equipment in which mass transfer occurs. Now, to further our understanding, let us look at some problems of interest in heat transfer. It is important that you try to appreciate the width of the subject, the breadth of the subject, before we really get into the equations which govern the laws, etc. I am going to look at three problems. First of all, I am going to look at a problem of heat loss through thermal insulation on a steam pipe. That is the first problem. Then I am going to look at a problem of heat transfer to water flowing through a tube. And then I am going to look at heat transfer in an electric furnace. These are three problems of interest in heat transfer, and we will look at them one by one. The first one, heat loss through thermal insulation on a steam pipe. Steam is widely used in manufacturing process industries. All of you know that. Suppose, let us say, I have a big plant with a lot of workshops, sheds all over, and steam is needed in each of those sheds. Typically, one may have a central facility where a steam generator is located, steam is generated, and there will be pipelines which carry that steam to the various sheds. Even within the shed, there will be long pipelines along the walls which carry the steam all along the length or the breadth of that shed, so that it can be delivered at a particular point where it is required. Now, we have gone to a lot of trouble to generate that steam in a steam generator. We will have burnt oil or something like that, given heat to water and raised that steam at the pressure required. So, here in this example, as you can see, we are talking of steam at 5 bar and 170 centigrade, superheated steam at this condition, and we are passing it through a pipe. Having gone to all the trouble to generate that steam, obviously, we do not want that steam to condense or lose heat, so we put insulation around it. Insulation may be in the form of some fibrous insulation like mineral wool, glass wool, etc., which is put round, and a certain thickness of insulation is put on the pipe. The question before the heat transfer engineer is, what should be the thickness of insulation to put? Now, let me just draw a sketch so that we will understand things better. Let us say, let me draw a graph. Let us say, in this graph, on the x-axis, I have the thickness of insulation. On the x-axis, I have the thickness of insulation, which is put around the pipe. Let us say thickness of insulation in centimeters. And on the y-axis, I have the heat loss rate. In watts per meter, that is heat loss rate per unit length of the pipe. Let us say when I have no thickness of insulation, there is no insulation on this pipe, the amount of heat being lost is as indicated by the cross here. That is the amount of heat being lost. Obviously, if I put insulation on this pipe, the heat loss rate is going to decrease. Typically, I'll get a graph something like this. As the more and more insulation is put, the heat loss rate, watts per meter, will go on decreasing. Now, the problem before the heat transfer engineer, who's to design this and decide what thickness to put, is the following. He is told, restrict the heat loss rate to a particular value, let us say given by this, as I am marking here. So, find the thickness of insulation to restrict the heat loss rate to the value specified here, in which case, having done this calculation and got this graph for a particular insulation that he is using, he will go horizontally, then go vertically and say this is the thickness of insulation needed. Or the problem may be in reverse. He will be told we are going to put 3 centimeters of insulation or 5 centimeter thickness of insulation. What will be the heat loss rate as a consequence? In which case, given a certain thickness, he will go up like this, having got this graph, to this graph, then draw a horizontal line like this and say this is the heat loss rate, and therefore from here to here, that is from this point which is the heat loss rate without insulation to the heat loss rate because of the insulation, this is the amount of reduction in the heat loss rate. You follow? So, because of his knowledge of heat transfer and heat conduction occurring in the insulation, the heat transfer engineer will be able to either decide on the thickness of insulation to put or find the heat loss rate for a given thickness of insulation. This is